Welcome to Endogenous Growth. We're doing Endogenous Growth. Hooray. Cool. So, what did we do last time? Well, we did the neoclassical growth model. We learned a lot about like dynamic programming stuff, and we learned a little bit of theory around the neoclassical growth model. I mean, ultimately, it's an improvement on Solo, and made a couple of tweaks um, in how it gets estimated, how we solve the model out, and stuff like that. And then there's a couple other things in there that describe the steady state behavior a little differently than the Solo model did. But there's a little shortcoming here. Growth was still exogenous. It still came from outside the model. It was still basically assuming, hey, we get lucky and boom, we have growth. But the countries that are richer than the poorer countries, it's not necessarily luck. There's other things that go into it, right? You don't just go, oh, hey, we got lucky and now, we are a richer country than poorer countries. There's things that go into it. There's investment. There's, there's human capital investment. There's assuming different types of like contributions that workers produce. Because before it was kind of just assuming like, well, the labor for, say, a PhD economist is treated the same as a manual laborer working as like an auto mechanic. But that's clearly not true. We produce very different things that produce very different types of value to the economy. I'm not saying one's more valuable than the other. It's just different, right? Because you get one guy producing just ideas and another guy producing things. And well, there's a big difference between ideas and things in terms of how they're contributing to the economy. You need both. But here's the thing, right? Like, it's also kind of assuming, well, the manual laborer working as an auto mechanic is the same as a manual laborer working in a sweatshop in like 1900. These are not plausible assumptions to be making. Similarly, there's no growth spillovers across sectors in the economy, right? One sector can innovate in a way that spills over into other sectors. Look at the advent of the computer chip. That spilled over everywhere, right? Everything has a computer chip in it now. So what gets developed in one sector of the economy then spills over and gets used by other sectors. Things like the neoclassical growth model can't really account for that. But if we try looking at endogenous growth models, maybe this class of models can account for that. So this time, what we're going to do is we're going to address some of the shortcomings of the neoclassical growth model, and we're going to try to improve on them. And we're not just going to go, oh, well, this sucks because this sucks, and then that's that. If you say something sucks, and you explain why it sucks, the next step is to try to make it better, to make it suck a little bit less. Now, the neoclassical growth model doesn't really suck. It's just we got some shortcomings, and we want to address those shortcomings and try to make them a little bit better. So the improvements here are really going to be less substantial than the improvements done to the Solo model as compared to the neoclassical growth model, which I mean, hey, cool, it's cutting edge growth at work here. You get huge steps and then eventually it kind of levels off and you get really small steps in improvements. And ultimately, the specification's not that different. You still have optimizing households with the natural log of C as their objective function. You still have a resource constraint, y equals c plus I, and investment's even still the same. So the only thing that's different is just the specification for output. And the math itself is almost exactly the same. So now you're going to be like, well, why are we spending any time on this at all? And it's because we're learning how even the smallest difference in the setup can make a big difference in the interpretation of the results. And thus, it'll affect the implications of the model, which are really more important than doing the math anyways. The math is just the means to an end. It's not the end in and of itself. So here's what we're going to be doing. We're going to talk about the assumptions of the model, talk about how and why production is different, and we're going to solve the model. I'm going to do dynamic programming. If you want to do a 2-period model along with it, be my guest. If you get the end result using a 2-period model as I get from dynamic programming, then you know you did it right. If you didn't, email me. I'm happy to help. The methods are going to be identical to the neoclassical growth model. Then we're going to look at steady states, talk about the results, analyze effects of shocks of the economic system. We're really going to be looking at the difference between anticipated and unanticipated shocks, and we're going to look at examples of each. And really, by introducing this model, we're going to see how endogenous growth might make a little bit more sense in terms of, kind of the economic intuition, right? If growth is coming from our individual choices and how well these results of our choices are being used by others, it makes a little bit more sense than just assuming some benevolent central planner from outside the model just gave us the technology to use. Maybe it's a little hyperbolic there, but it makes more sense to assume that growth comes from within the model rather than from outside as just a chance of just a stroke of luck. So we've got the same utility function, right? U equals the sum as t goes from 0 to infinity of beta to the t of the natural log of CT, or consumption. We still want to maximize consumption subject to a constraint given by our resource constraint in equation 2, y equals c plus I. Let's see, here we go. Investment is still given by the flow of capital, or the law of motion of capital. Output is the different one. And it's not even all that different. There's just a little bit of a difference in that exponent there. Y here is equal to a times k to the alpha plus eta. Right? That silly looking n is not an n, it's an eta. So y equals a times k to the alpha plus eta. Well, alpha, remember, is capital's share of income. So we know what alpha is, but what's that eta term? What is that? Well, okay. So in the neoclassical growth model, production was actually this, because I don't know how to fix anything in post, so I just kind of, hit pause and then fixed it, and here we are. Then I pushed on pause. So this is what the production for the neoclassical growth model was. Y equals a times k to the power of alpha, where alpha is is capital's share of output. Now here it's y equals a times k to the alpha plus eta. Eta gets added to that alpha exponent. What this is this is spillovers in production. So this is like a set of knowledge externalities that get generated among individual firms. So if a firm figures something cool out and it can get used somewhere else, other firms use it in their production. And it can be the case where, say, alpha plus eta is greater than 1, and then you'd have increasing returns to scale in production. So as per usual, I just kind of substitute everything into that resource constraint, and that gives me a times k to the alpha plus eta equals c plus kt plus 1 minus 1 minus delta times kt. And then solving it for ct, well, I just basically just subtract that kt plus 1, and I add 1 plus delta kt to the other side, and that gives me ct equals at times kt to the alpha plus eta minus kt plus 1 plus 1 minus delta kt, right? So that's output minus investment, right? The pink minus the blue. Output's pink, investment is blue, pink minus blue, output minus investment. Okay. So now I can formulate my Bellman equation, which is just v of kt equals the natural log of c plus beta times v of kt plus 1. So I'll just plug c in. C equals that resource constraint, or I guess output minus investment. Plug that in for c in the Bellman equation. So that gives me equation 8, right? V of kt is a natural log of a times k to the alpha plus eta plus kt plus 1, or minus kt plus 1 plus 1 minus delta kt plus beta times v of kt plus 1. I take my derivative with respect to kt plus 1. That gives me 1 over ct times negative 1 plus beta times the partial of v of kt plus 1 with respect to kt plus 1 equals 0. All right, so this actually, equation 9 here, this isn't any different than what we've seen from the neoclassical growth model. So I can add 1 over ct to both sides. All right, well, it's 1 over ct equals beta times that partial thing. What's that partial thing? Well, I got to figure that partial thing out, don't we? So I take the derivative of v of kt with respect to kt instead of kt plus 1, and and I update it one period. Right? So the derivative of v of kt with respect to kt is given by equation 11. So 1 over ct equals alpha plus eta times a times k to the alpha plus eta minus 1 plus 1 minus delta, right? Originally, in the neoclassical growth model, it would have just been alpha times a times k to the alpha minus 1, but we've got that eta in there now. So it's alpha plus eta, right? Alpha, capital share of income, plus any sort of knowledge spillovers that can move from one industry over to another. But really, even this isn't all that terribly different. If I update it one period, well, the process there is the exact same as what we had with the neoclassical growth model. And if I plug that in to that first order condition that I had, this is what I get. So this is my Euler equation for capital. And this looks pretty familiar, doesn't it? 1 over ct equals beta times 1 over ct plus 1 times your stuff. And that stuff is the marginal product of capital plus 1 minus depreciation. So if I solve that out, well, how am I going to solve this one out? Well, what I'm really interested in here is just that ct plus 1 over ct. So I just multiply both sides by ct plus 1. And this is the extent of the math that we need for this chapter, because this is now in a form that we can look at, we can study, we can analyze, and we can get really interesting stuff from. Because, well, now we've got a specification that's different from just the standard constant returns to scale neoclassical growth model thing. This is going to be a little different. And because of that, well, we can get more interesting results. So remember, in the neoclassical growth model, where we had those constant returns to scale, right, we would have, or at least what would be getting us set up for the steady state, not necessarily in the steady state, because this is still t and t plus 1 stuff. It would have been ct plus 1 over ct equals alpha times beta times at plus 1 times kt plus 1 to the alpha minus 1 plus 1 minus delta, well, equals 1, because ct plus 1 and ct, when they're equal to each other in the steady state, gives you that. So really, in the only way that we could see any form of growth would be from a sub t, which is assumed to be exogenous. It comes from outside the system. So another way to think of it is just growth happens when you get lucky. Now, I hate to quote that Two-Faced guy from the Batman movie. He's like, I'll make my own luck. Maybe an economy doesn't want to get lucky. It doesn't want to rely on luck for growth. Maybe an economy wants to rely on its own luck, make its own luck. Because, well, in the real world, you get actual measurable innovation. Like someone invents something really cool, and then it gets picked up by other industries. And so when you get some really awesome innovation, some cool new invention that other people go, hey, I can use something like that. Now, they can't maybe use the exact same thing, because that would be theft, but you can maybe take the idea, the process. Electric cars, they've kind of been a thing for a long time. They've really been taking off lately. So, the first electric car comes out and it starts getting used, fairly regularly, and it's offered at a decently-ish low price where at least, more than the super, super duper ultra rich can afford it. Other guys go, maybe that's not a bad idea. Maybe I can do something with that too. And then you get more electric cars. I'm still partial to the internal combustion engine myself, but electric cars are, at least they're fun to drive and they're fun to ride around in for sure. Those things go ridiculously fast. It's awesome. But that's like, okay, something somebody starts producing and other people go, hey, that's kind of neat. I like that. Maybe I'm going to try to do that too. Another would be the, for, any guitar nerds, hopefully there's somebody here who plays guitar, with like digital amp modeling. Well, at first digital amp modeling kind of sucked. And the idea is you get like it's like basically a computer that mimics the sound of a real guitar amp. And for the longest time, they kind of sucked, but lately some of them have been pretty good. Let's say, I think the Axe FX came out first. So the Axe FX comes out, and that thing's actually pretty damn awesome. You almost can't tell the difference between a real guitar amplifier and this thing. And then I think the Kemper came out after that. All right, so that's, they're slightly different technologies, but, you see one go, oh, that's freaking awesome. I'm going to try to make something like that myself. So that's kind of where we could see this innovation in the economy. And so, in those cases, it got picked up within the industry, but there's inventions that can be picked up by other industries as well. A great example is that movie, The Founder. Watch that. There's a great scene where they talk about like trying to put a burger together. That's basically the conveyor belt, or the I'm going to work on something and then hand that over to somebody else who works on it. And it started with like cars, like with the manufacturing line, and now pretty much everything is produced that way. Multiple industries took that particular process, which I believe started with Henry Ford, but I could be dead wrong on that. And multiple industries have picked that up. It's no longer just cars; it's airplanes. It's sure probably computers are made that way. A lot of things are made that way. So yeah, that's kind of what that innovation could be. Anyway, so this time, because there's that measurable innovation in the economy, well, we want to be able to account for that. So that's what that eta term is. So now I've got CT plus 1 over CT equals alpha plus eta times beta times AT plus 1 times KT plus 1 to the alpha plus eta minus 1 plus 1 minus delta. Now, it doesn't necessarily have to equal 1 like what I had with equation 15 here. Why is that? Well, it's because there's now 3 cases. It could equal 1. There's that case, but there's other cases as well. It could be less than 1. It could be greater than 1. And because we've got these possibilities, maybe we need to talk about all 3 of these possibilities. So I've got 3 cases to consider. Let's do one more thing. Let's set that Euler equation equal to gamma with a little c subscript. Right, so that CT plus 1 over CT equals alpha plus eta times beta times AT plus 1 times KT plus 1 to the alpha plus eta minus 1. Alpha plus eta minus 1 now. Voila. Another change that just happened like magic out of the blue. So alpha plus eta minus 1 plus 1 minus delta equals gamma sub c. So gamma is going to be the growth rate of consumption, because if you've got CT plus 1 over CT, right, think of that as the growth rate over of consumption. If CT plus 1 is larger than CT, well, then consumption is increasing. That's the growth rate of consumption. That's going to be equal to the marginal product of capital times beta. So with that in mind, right, we can talk about 3 different cases here. Each case is going to be talking about a learning externality. So the effect of that eta term is going to be causing us an externality of learning, meaning you do something cool in one industry, another industry can adopt it, and it can help that one too. So like, I was talking about stuff with McDonald's and The Founder. Great movie. If you haven't watched The Founder, you definitely need to go watch The Founder. It's really awesome. Really interesting movie. Anyways, so now we're first going to find ourselves searching for a world where the growth rate of consumption is less than 1. So basically in English, it means I want a growth process where beta times the marginal product of capital is less than 1. I don't know why it says less than 1, which would be implied by the fact that alpha plus eta is itself less than 1. And it would tell us the effect of knowledge spillovers, eta, isn't large enough to counteract the effect of the alpha minus 1 of decreasing returns to individual capital accumulation. And that the long-run growth rate is 0. Now, this is similar to a case of like the Solow model or the neoclassical growth model, in which case there's no technological progress or population growth. Now, if you want technological progress, okay, well, now AT plus 1 is larger than 1. But in the event that A is just 1, right, you get no other progress from there. It's just, well, everything converges to a steady state. So if K were to increase their investment in this case, say, above the steady state value for K, then the growth rate of the economy would turn negative. Why is that? Well, it's a decreasing function of K, right, at this point. So therefore, the economy returns to its steady state like what we saw in Solow. If you increased steady state capital, or if you increased capital above its steady state in the Solow model, we saw that it would converge back towards where it was in the steady state, because with steady state capital being above, or sorry, with capital being above steady state capital, right, you end up with this economy that's like, okay, well, we're going to save a little bit less. And as they save a little bit less, the amount of capital sort of converges back to its steady state. And, think of an invention like the shake weight, right? This thing gets made, doesn't really generate any spillovers to other industries that we could look at. It just kind of sucked. Now, do you remember what the shake weight is? It was this thing. You'd hold it, and like the two weights on either end would like shake, and it was such a stupid thing. I guess really the only industry where this invention could have spilled over was like to the comedy industry, where people made fun of it relentlessly. I think there's like a whole like South Park episode making fun of this damn thing. Oh, stupid. Anyways, all right, so that would be a case of equation 18, where gamma sub c is less than 1. So if capital were to increase above its steady state, right, the growth rate of the economy turns negative for a minute. The amount of capital that we have falls. The rate of capital accumulation falls. So the amount of depreciation of capital kind of takes advantage of that and brings us back towards our steady state capital. And there's no spillovers to any other invention, or from one invention to industries with another. However, let's look at case 2. Case 2 is another sort of, I guess, like extreme end case, where instead of that growth rate in consumption being less than 1, here it's greater than 1. In English, this means we want a growth process where beta times the marginal product of capital is greater than 1, in which case alpha plus eta would be larger than 1. Here, learning spillovers are more than sufficient to offset the diminishing marginal product of capital. Learning externalities here are so strong that it forces the economy into like this ever-increasing growth rate. It just kind of keeps growing and growing and growing. And this happens because there's, say, a unique steady-state capital stock, but it's not stable because gamma is an increasing function of k. So if k were to rise above the steady-state value for capital, it just keeps increasing. It's an explosive growth case. Now, you'd like to think this is preferable because you get a lot of growth, but no, because it doesn't really make sense when we compare it to like real-world data. Yeah, we have exponential growth. This is applying that like the growth in this model will be more rapid than even what we actually observe. So is there something a bit more realistic? Because here we don't have a stable growth path. Maybe we want something that's a little bit more stable. We want a stable solution. We want a stable growth path. We want a growth path. We don't just want a flat line, but we want it to be stable. And that's where we have case 3. This is like our Goldilocks zone, where beta times the marginal product of capital is exactly equal to 1. And it's implied by the fact that alpha plus eta equals 1. So that exponent is equal to 1. And it's what's known as a knife edge case, where learning externalities exactly compensate the decreasing returns to individual capital accumulation. So here, the aggregate production function becomes what is known as the AK model, where y is a times k. There's no to the alpha or anything like that. It's just k to the power of 1, which says we have like a long-run growth rate in a model with substitutable factors and full market clearing. In other words, as capital increases, output increases in proportion. So even though we've got continual full employment of labor, there's sustainability in the production function. So any sort of cool new idea generates knowledge spillovers to other parts of the economy. So you get like, say, an increase in savings, hence investment, increases the growth rate permanently, even though output per worker still grows at like a positive rate. And we have what's known as a balanced growth path, where everything grows at the same rate. And so an innovation in this economy is beneficial. Saving rates would be shifting to keep us on the growth path rather than exploding with growth, which means an idea from one industry can then move to another and make everyone even much more betterer than they were before. A good example that I've used previously is a computer chip. It gets developed. You can use it in aeronautics. You can use it in phones, computers, robotics, terminators. Yeah, that worked. So when this happens, by the way, sorry about this stuff here. I LaTeX oopsie. So when this happens, we can put more into that industry because it pays off even more and more than it did previously. And the more we invest, more it grows. And the idea is that the more researchers we have, the more research we get. So, with a bigger economy, you can have more scientists. And with more scientists, you get more discoveries, which means faster growth. So, as long as eta is greater than 0, you have spillovers and growth in K, and then A kind of like accelerates like forever. Endogenous growth occurs in the case where the economy sustains positive growth even when there's no exogenous source of growth. So, like, a big thing to consider is like, why would we have all this research and development? Because if you've got research and development and a model of perfect competition, price equals marginal cost, and all the R&D costs are essentially sunk costs, and there's no way to recoup your investments. So if you have a model like this, there's a big thing you need to consider, and it's patents. Intellectual property laws. They're important in this model to make sure there's an incentive to do the research and development. Because why are you going to do the research and development if the product that you make then hits the market and everybody else can take it and run with it, and then the price, falls to marginal cost, and you're like, great, I just sunk billions of dollars into the development of this project, and everybody else gets to take the idea and run with it, and I'm out billions of dollars. So Romer in 1986 suggested that there could be various forms of government policy that could spur economic growth. So, I might talk a lot of shit on the government, but there are times where they can improve things. And in this case, they improve things by generally staying out of the way and maybe enforcing some intellectual property laws along the way. So that's going to wrap up this lecture. I guess it was a relatively short lecture. That's all the math that we need to do for this chapter. So now we're going to talk about shocks and some applications of endogenous growth theory in the real world. So next time we're just doing graphing and a little economic intuition, and that's it. And we can see how the applications of endogenous growth can explain what we're seeing in the real world for growth from a lot of these examples. So yeah, that wraps up this stuff. Part 2 comes on Thursday, so be on the lookout.